In the last video, we took a look at the analog oscilloscope. Today we're going to take a look at the digital oscilloscope, and rather than using an Arduino to generate signals for it, we're going to use something slightly more advanced, the function generator, also known as the signal generator. So before we dig in, let's take a look at some of the things that this function generator can do for us. The function generator, depending on who supplies the function generator, will have different looking dials and buttons and switches, but they'll all do pretty much the same thing. Let's zoom in a bit closer right there. The most important one is probably going to be your power switch right here. And when you turn on the power switch, you'll see that a display should pop on, and numbers should pop up on this screen right over here. You've got a nice dial on here that you can spin back and forth, and you can see that makes the numbers change. And the numbers that are being indicated right here are either in kilohertz or in hertz. And again, kilohertz and hertz is an indicator of frequency. So a kilohertz means you repeat the signal 1,000 times per second, and a hertz means you repeat it once per second. So right now, this is telling me we've got a signal of 5.72 kilohertz, so it's repeating 5,720 times per second. Controlling that, I've got these range buttons right in here, and right now I've got the 10K button pushed in. So when I spin this dial, that gives me a range of 0.17 as my lowest frequency, so 170 hertz, okay, because 0.17 of a kilohertz would be 170 hertz, all the way up to about 24 kilohertz. This is approximately the range of human hearing, and within that range you can create a lot of really annoying noise. If you want higher frequency signals, now you can hit the times 100K button, and you can see that, well, it's 10 times faster. So we're getting 229 kilohertz. And if you come up here into the megahertz function, we're now getting 2,251 kilohertz or 2.2 megahertz. And these frequencies start getting into the radio frequency range. So if you had an antenna hooked up on there, you could be transmitting a radio signal. And if you did it with a lot of power, you could be jamming some radio signals and getting in trouble. So let's go back down into the audio range. Let's go down into the 1K range. Actually, let's go down even lower. Now you can see we've got the hertz button turned on. So right now we'll be generating a signal of 222 hertz. We'll listen to hear what that sounds like in just a moment. In fact, you can keep going down, and 21 hertz, which is sort of at the low end of human hearing, and you can go even lower, all the way down to 1 or 2 hertz, 1 or 2 cycles per second. That's like on, off, on, off. So we've got these different signal frequencies that we can dial in right here, and just keep an eye on this dial and it'll tell you 208 hertz or 2.18 kilohertz, 2,180 hertz. So there's a few other things that we can make this do. Over here, we've got different waveforms that we can generate. Now, the most common wave that we work with is usually the sine wave, and that's that S-shaped one right there, the nice smooth transition that we'll show you in the oscilloscope. But you can also get a sawtooth waveform or a pulsed waveform. And the pulsed waveform is what we were seeing on the Arduino, where it comes in and it turns off. This one actually has a negative range on it. We'll talk about it in a little bit. So it doesn't just go off and on. This one goes from positive voltage to negative voltage, which sounds kind of fancy, but really it means it's pushing the voltage out sometimes and it's sucking it back in at other times. Push, pull is what it's going to be doing right there. And again, we can play with that. Let's go back to the sine wave. We've got some dials that we've got right on here to talk about. So when you're talking about signals, you've got frequency, which is how quickly the signals repeat, and then you've got amplitude, which is how high up the signals go. And so we can dial this in and we can change our amplitude, and we'll give you a real sensible reading sense for what that means in just a moment. So we also have marked right down in here ATT 20 decibels. And we can talk about what 20 decibels mean, but this means attenuate. And just as amplify means to make a signal stronger, attenuate means to make a signal weaker. So this is going to make the signal weaker by 20 decibels when it's pulled out. If you push it in, expect your amplitude to go up and your signal to get quite a bit louder if you're hooked up to a speaker. We've got something called the DC offset. We can play around with that in just a moment. It'll make more sense when we can see it on the oscilloscope display. Symmetry will allow you to tilt and twist your signal and warp it a little bit back and forth. And again, you'll see what that looks like on the oscilloscope, and we'll hook it up to a speaker so you can hear that. Both of these say that you have to pull them to get them to turn on. So neat little switches right here. You pull it out to turn it on, push it in to turn it off. Okay, pretty cool style of switch. Over here is another really cool style of switch, and it's for sweeping. Now, sweeping means start at one frequency and go to another. And if you look right here, you can control the rate, how fast it does the sweep, and down here the width, what frequency band it sweeps across. So you'll notice right here, I'm at a fixed frequency because I've got this inner dial in the off position down here. But if I turn that on and I turn it up, now you'll notice that the frequency automatically starts to change. So if you want to cycle through a range of frequencies by spinning that dial all the way over here, you get the widest possible range of frequencies. So you see it starts low and then goes high. And by changing this dial, you control how long it takes for it to happen. So right here, and I crank it all the way over this way, you can see it's taking me a long time to cycle up through the frequencies. And when I spin it down this way, it's blasting through those frequencies really fast. Now, just looking at that doesn't mean anything. What we'll do is we'll hook it up and we'll listen, and we'll take a look at what that's doing on the scope so we can take a look at some of these signals. But those are the key buttons on your function generator. Your function generator is going to hook up with a cable. And let me just back out a little bit here and adjust my view. Still learning the controls on this little device. There we go, and now you can see that we've got the oscilloscope down below, and we've got a cable to connect right in here. And again, this cable comes in with a BNC connector, but instead of coming out like an oscilloscope probe to a fancy probe, this just comes out to a couple of alligator clips. And again, we're doing that and using the BNC connector and the shielded cable because at our high range of frequencies on here, we can get up into the radio frequency range, and we don't want to start transmitting radio waves unintentionally. By putting the shielded cable around the outside, that keeps the signal inside from acting like an antenna. This plugs into the ground. Now, there are other features that we can do on here. We can synchronize two function generators together by hooking them up together, but we're just going to use the output for right now. And what we're going to do is we're going to take that output, and I've got a speaker sitting right down here, and let's take a look right there. We will hook the two signals in right here. Now, it's important, you can see I've got a now, let me take the oscilloscope probe off there, and then I can talk about why it's important to hook the oscilloscope probe up correctly later on. Let's just hook this in right here, and we'll go one to right there. And in the background, you should hear a whooping noise coming through right there. Let's just put the speaker down here. And hopefully you're enjoying that as much as I am. I'm sure the people out in the hallway outside my lab are really wondering what's going on. Hey, it helps with maintaining social distancing when you have a noise like this going on around you. Okay, let's just zoom out here a little bit so we can see some of what's going on there. And let's take a closer look at the dial right on there. And so you can hear the sweep going in there, and you can hear the frequencies changing. And as I change the rate, now you can hear a good 1950s space sound effect. And if I dial this back a little bit, I don't get quite as much of a range of sweep. And if I turn that off entirely, now the sweep is completely gone. If I change one of these buttons up here, now the sound goes away because I'm up at 22 kilohertz of sound, and that's just beyond the range of human hearing. The range of human hearing goes from about 20 hertz up to 20 kilohertz. And my headphones are certainly canceling anything out in there, and the microphone would be filtering out anything in that range. If we come down here, we swap down, and now we're at about 209 hertz. We should be getting a little bit of sound coming out of here at that. Let's bump up our amplitude. And there's a very low frequency buzz coming off there. Really curious how that's going to sound when I come back and take a look at the video later on. Alrighty, so that is a sine wave signal that we're taking a look at, and we can see it at different frequencies. If we want to dial that frequency back, or sorry, that amplitude back, we can just spin this dial right back in here. And if we really want to quiet it down, we can pull that out because that attenuates it. The exact opposite of amplifies it by those 20 decibels. Let's take a look at our digital scope now and take a look at what the digital scope can do for us to help analyze those signals. The digital scope has its on-off button in the top corner, and let's zoom in on the face while it boots up right here. So this is a 4-channel digital scope. And so you can see we've got a probe already plugged into channel 1. We've got channel 2, 3, and channel 4. Generally for a high school electronics shop, a 2-channel scope is more than sufficient. When your scope starts up, it does some self-tests, so it takes a few minutes to start up. And it says push any other button to continue. Well, it'll get impatient, and if it takes you a little while to push the button, then things will happen here. Now you'll notice our display is a lot more complex than what we might be getting from a regular analog scope. I'm just going to turn off the signal generator because it's really annoying, and let's take a look at what's going on this display. Okay, so right now I've only got one of the channels turned on, and that's the yellow line that we see coming across the line right there. And if I turn other channels on by, for instance, pushing the channel 2 button, channel 2's on there right now, and now you can see a blue line because blue is channel 2. And we can go through and we can add channel 3 in there, and you'll get a pink line, and I'll turn that off again as well. And let's go back to just the channel 1 menu. Let me just make sure. Oh, channel 3 is still on. Go away, channel 3. There we go. So this scope's working just like the analog scope did, but you can see there's no numbers on the dials over here. The numbers all show up on the display screen. So in the bottom corner right here, you can see I'm at the 200 millivolts per division scale. Well, our volts go up and down. So right now I'm at 0 volts, so this would be 200 millivolts, so 0.2 volts, 0.4, 0.6, 0.8, and this would be minus 0.2, minus 0.4, minus 0.6, minus 0.8. Right here you'll see my time scale, and this is quite a bit faster than we're going on the analog scope. We're on a 100 microsecond time scale. The time scale is controlled by a dial over at this end right down here, and so when I turn that dial, now you can see it's 250, 500, 1 millisecond per division, 2.5, and we can keep coming out. until we reach our slowest speed. There's 500 milliseconds. There's 1 second per division. And this goes, as you can see, quite a bit slower than the older analog scope, because it doesn't need to keep scanning that dot across the screen. This is a digital display. It's just remembering data. And to make this work, we're just changing the LCD crystals on and off in there. So the advantage of going to a digital display is pretty significant. Let's just get this centered a bit on the display right there, and come in a little bit closer. Okay, so there we go. This is a really slow display. It's taking 10 seconds to go 1 division. It's going to take me 100 seconds to go across the screen. So let's speed this up a little bit. And now we can see it going across the screen faster and faster and faster. And it looks like we've even got a little bit of a signal going in there. Now, the signal is already plugged in. We've got a scope probe plugged into channel 1. And the scope probe right here has a piece of tape on it for some reason. Let's get rid of that. Works just like the other one. The end can pop off right here, pops back on. Be really careful to not lose those or misplace them. If you take them off to do a probe, put them back on at the end of the day. Our ground is sitting right out here, and we can connect that to ground. And you'll notice that this one also has a little dial, little slider right on here that gives us a choice of X1 or X10. A little harder to see, but you can see that right on there. And we're in the X10 position. Now, when I come to channel 1 menu, so press the channel 1 menu and that appears on there, you're going to see a whole bunch of different options for channel 1. And to control channel 1, you push these buttons while the channel 1 menu is up. And right here, we've got a setting for our probe. So if it was set to X1, we'd have to push that. And this takes it in here, and it tells us we're measuring voltage, and we want our attenuation at 10x. That's all good. You can press this button a couple of times, and you can change that, because you can put all sorts of different scopes in there, but leave it set to 10x, because in our shop we're going to be using 10x probes almost all the time. Okay, so that's the channel 1 menu button, brings us in right here. Later on, we'll talk about what the coupling is for. You've got a few different choices, but we want to leave it in DC coupling for right now. If you're not seeing any signal, it might be because you're either in AC coupling or just hooked to ground, which gives you a perfectly level reference level. So if you want to be able to set your little zero line exactly to ground, you can set this to ground, and you can zoom in on it as close as you want, and then you can adjust that position right to 0. So if you want to get some really precise measurements, you can dial that in right like so. Okay, so now we've got that set to ground. Bandwidth limit, not really critical for what we're doing today. Our volts per division, again, course settings perfectly fine for what we're doing, and we don't need anything inverted. So there's a good set of settings that you can take a look at when taking a look at your channel menus when you go to turn them on. There's a whole bunch of other settings and functions right up here. The one I will mention that's kind of important is the run stop button. You can see right now this says it's recording, it's in auto mode. If I press stop, it stops recording. That'll capture whatever's on the screen so that you can analyze it a bit more. There's some fancy analysis tools, but if it says stop right there, just press the run stop button and it'll start running again, and you'll be back into your normal mode. This is what you should basically be seeing on your screen when everything's working really well. Again, a lot more power in this scope than in the analog scope, so a lot more ways that you can set it up wrong. Let's take a look at what it looks like when we hook it up to a signal. Okay, so we've got our signal generator turned off right now because that whining sound coming out of there was getting annoying, even with my noise canceling headphones on. When I go to hook up the signal, it is important that I pay attention to where the black line is coming off of here, because the black line here is hooked up to chassis ground, and this is also hooked up to chassis ground. So technically this wire is already connected to that wire, but they're connected out the back of the device and around through the building electrical system. And basically, if I connect this one to right there, then I'm going to short out my meter and it's going to give me a problem and not work nicely. So let's just connect right on here. It's always nice to have a good connection to ground. And I'm going to connect right up. Well, we could connect right here. We don't have to go all the way to the speaker. And again, I just take that little probe, hook it over the wire, and let it clip on. Don't let it get onto the insulated parts right there. Move that wire out of the way so you can see what's going on. And now I should see on the oscilloscope screen the visual representation of the sound that I'm hearing. Okay, I'm just going to come in on these parts right here and forget about the speaker for just a moment. And let's make some noise and see how that looks on our oscilloscope display. Well, there we go. We've got that turned on, and right now I'm not seeing a whole lot come through. Remember I said that we don't want our coupling to be on ground? Double check that. Now we go back to DC, and now there's a big blurry yellow line running across the screen. Now what that's telling me is that this frequency is so high that at the 25 milliseconds per division rating, it's going up and down and up and down and up and down so fast that it can't actually discern what's going on. So what I need to do is I need to change my seconds per division, and I need to zoom in horizontally. And as I do, you can see that waveform starts to split out into a nice, beautiful sine wave. Now, if I dial this, let's get this set to exactly 2 kilohertz. Went a little too far. Touchy, these analog devices. There we go. That's pretty good right in there. Now, that's got us with a 2 kilohertz signal, meaning that we should see 2,000 complete sine waves every second. So when I talk about a hertz, that's how long it takes to go from one high point right here down to the low point and back to the high point. And so if I'm doing that 2,000 times per second, that should be 1/2000th of a second that I'm looking at. Let's time how long it takes it to go. We're on a 100 microsecond scale. So if I start right here, this is 100 microseconds, 200 microseconds, 300 microseconds, 400 microseconds, 500 microseconds to complete one complete division right there, or 0.5 of a millisecond. Take 0.5 of a millisecond, go 1 divided by 0.0005, and you should come out with 2,000. So we're getting 2,000 of those coming through every second. Now, it's frozen on our screen because we have something called a trigger. And our trigger is this little yellow line right here. And we were using it on the analog scope. It's just a lot easier to see on here because we can display more information on this display. And I can move that, I'm moving the 0 line back and forth. I carefully set that. Sorry. I can move that little line up and down. Oh, I'm moving the horizontal right there. I'm moving horizontal right there. This is a new scope to me. They moved the trigger position to right here. And so the trigger right, it says trigger on it. And I can move that up and down. And if I move it too high, that starts moving back and forth because it doesn't know where it wants me to freeze the display. I've got to bring this down right in here. And now you can see where it is hitting that line right there is where we're freezing that display. And then I can move that horizontal position back and forth, and there we go. We're meeting right in there. Let's move that display down a little bit. There's our trigger menu. And if I come right down here to the 0 volts, and let's go to the trigger menu. And so right now it's got different types of triggers, so we can look for an edge, which is better for a square wave. Let's set it to, let's leave it on edge. Oh, there we go, rising edge. We can have it on the falling edge. And this signal is changing. It's still the same signal. It's just starting at different points. And we're in auto mode, and we're coming off of channel 1. So this is all really good. You could set the source of the signal to be any of your channels. So if you're trying to synchronize 2 signals, you could do that as well. You can also see now that we've got a fairly constant signal going on, that it's actually measuring for us right down here, and it's telling us it's coming in at 1.99146 kilohertz. So a little more precise than what we're seeing right up there. So there's some really neat stuff going on right in here. Now, a lot of this seems pretty complex to set up, and it is, and it's worth learning how to set things up and how to control the scope. But there is a cheat button, because of course there's a cheat button in the digital world, and that's auto set right up here. So if you come in and you've got a brand new signal, and it's, let's just spin some dials right here. So there we go. We've got 50 volts per division, so we can't see it there. Let's change our timing so that that's all messed up right there. And you just press auto set. Auto set will read that signal, and it will come in here, and it will tell you all sorts of information about it. It will tell you the peak to peak of the signal is 524 millivolts. So from right here to right here is 536 millivolts, or about a half volt. The period, how long it takes for one signal to complete, is 500 microseconds. We already measured that the old-fashioned way. Our frequency reading is right here, a few more digits right down there. And this also gives us something called the RMS voltage, which stands for the root mean squared voltage, and we'll talk more about that when we're looking at our power supplies. So auto set flashes up a display that has some really neat information on it as well. Let's go back to our channel 1 menu. Before we do, basically you just want a continuous wave in here. It's got other fancy features, one called a fast Fourier transform, which is really cool, but we're not going to get into it today. Okay, we're back at the channel 1 menu. We might want to see that in a bit more detail. So again, we can zoom in based on time and on voltage, so we can see more detail on the voltage, or we can see less detail. And of course you can measure the peak voltage by going, we're at 100 millivolts right here, so this is 100, 200, about 250 millivolts down there, and this is minus 100, minus 200, minus 250 right in here. So that was the voltage that you were looking at. Let's play with the dials up here and see what happens when we start changing things. So right now I've got the amplitude turned, the attenuation turned on. Let's crank the volume. Okay, when I push that in, we stopped attenuating the signal, and you saw the amplitude jump up quite a bit in here. Now the frequencies remain the same, but the voltage has jumped up a lot. So to see that entire signal, I need to change my voltage setting. Now I'm at 1 volt per division, so this is at 1 to 2.5 volts. So a significant jump in the voltage difference right there just by switching that button. And if I turn it up higher still, the sound's going to get louder and louder and louder, and that's because the voltage that's driving that speaker is higher and higher and higher, or lower and lower. So right now I've got it set to 1 volt per division. I can probably zoom in on that a little more closely if I need to measure it more precisely. So we've got time and we've got voltage. Now, as I was saying, there's a number of different things that you can do with your signal generator. You can come in here, and instead of using a sine wave, you can go to a sawtooth or triangular waveform. And that waveform right in here, as you can see, is very zigzaggy. And you can also go to a pulsed waveform, which is more reminiscent of what you'd get if you were looking at the signal that is coming off of your Arduino. On, off, on, off. This is pretty close to a digital signal. You will see this little spike right at the end right here, and there's some good electrical and mathematical reasons why that spike is happening right in there. It's very difficult to jump a voltage from right here to right there and stop at that exact point. And so quite often when you see a signal, there's a lot more going on in there than you think at first, and an oscilloscope's a really good way to get a look inside and see what's going on with that signal. Alrighty, what else can we do on here? We talked about, let's go back to the sine wave right here. That's a slightly less annoying sound. And let's take a look at our DC offset. So if I pull that on right there, okay, that completely disappears off the screen because I'm cranked all the way over to positive. Let's bring that down. And if I put it straight up and down, I'm at 0 DC offset. So there's not much change in the voltage when I look at it like that. What this lets me do is right now, my voltage coming out of the signal generator is between, I'm at what, +2 to -2. If I move it up here, okay, I need to adjust my trigger level so that I capture that and freeze it. Now I'm coming from 0 volts up to 1, 2, 3, 4 volts right on there. So now instead of going from -2 to +2, I'm going from 0 to 4. Okay, let's bring this down a little bit right here. And now our DC offset, again, our trigger level needs to be adjusted. And we can bring that right down in there. And now we're going from 0 to -1, 2, 3, 4, down that way. Oh, sorry, we're at 500 millivolts, 0.5, 1, 1.5, 2, from 0 to -2. And of course, that was 0 to +2 right up there. So if I push the DC offset in, we come back here, and we're locked on the screen. Now the symmetry, if I leave that right up at the top and pull it out, I shouldn't see much change. But if I twist it this way, you can hear a different sound, and you can see that the entire sine wave has shifted to the left. If I turn it that way, it shifted to the right. So you can play around with some of your signals right on here, and it's interesting to see what some of them look like. And it's definitely making a difference in the sound as I run those back and forth. What it's doing for me in here is it's really playing around with the duty cycle of that pulsed signal. Again, back to our standard sine wave. Turn off the offset, turn off symmetry. Oh, sorry. Push them both in to turn them off. Alrighty. Now the sweep is kind of cool because, as we said, that changes the frequency as we go through there. And now you can see that we get the original frequency, but then it shifts, and each time it goes through, it's seeing a slightly different frequency, so it's really hard for it to get a measurement on one exact frequency because it never stays at the same frequency for very long. Our trigger is set up so that we always freeze it right in the middle of the screen. But it's now displaying us a whole bunch of different frequencies, and you can see that some of them, the lower frequencies, are quite long and have this long slope coming right out in here. We can change the range of frequencies that are appearing in there and how fast it cycles between them. And if I slow it right down, zoom out a little bit here, you can see it starts out with a low frequency with those long waves and brings it together right in like so. So you can get some really neat sounds. Just in case my mic's filtering those out, now this piece of equipment is analog. It's not brand new. It could be out of the 1960s, and you probably recognize some of these sounds from old TV movies, old sci-fi movies. And that's because they were funky sounding sounds in the 1960s and 50s and 70s when this is what the state of technology allowed them to generate. Let's turn this off for a second because that's really annoying. Now, I've also got right here another cool little device. I've got a microphone. And what having two channels allows us to do is it allows us to compare an input signal to an output signal. So I can have my input going into the speaker, and then I can see what comes out on the microphone. And it's going to be a much attenuated, much weaker signal. So I'm going to plug this into channel 2 right here. And I can now compare channel 1 and channel 2. To get channel 2 to show up, I press the channel 2 button. There's a blue line right there. Now what I'm going to do is I'm going to move channel 1 right up there. So that's my 0 line for channel 1. And I'm going to move channel 2 down. So that's my line right there. So now I've got a 0 line right here and a 0 line right here. I'm going to look at the two channels, this one on the bottom half of my screen and this one on the top half of my screen. So if I go ahead and start that up, there's my, let's turn off that sweep. Let's just go with one standard signal. And let's bring that voltage down so it's not quite so annoying. And we'll freeze that right there. Now they both have to share the same trigger. Now right now, I don't see very much coming through on channel 2. If I put the speaker in, microphone in really close to the speaker, I'm still losing a lot of data, but that's because both of them are set to 500 millivolts per division. This is coming straight off the signal generator, so it's a very strong signal. This is an unamplified signal coming off the microphone. So let's zoom in on that as close as we can. And you can see I'm turning this dial right down here to 100 millivolts, 50 millivolts, 20 millivolts per division. And that is the finest that I can get right on there. And at this frequency, at 2 kilohertz, that's not showing up particularly well on the microphone, but you can see that these two signals match each other pretty closely in terms of their frequency. Let's see what happens if I turn the amplitude up a little bit. There you can go. Now they are a little bit out of phase with each other. That's because when the signal comes off here, it generates a pulse that hits right here. There is a little bit of time lag as that transmits from the speaker into here. Yeah, they're about the same frequency. Let's confirm that for sure. Let's try changing that frequency up and that frequency down. And you can see that the two signals are working together, but the raw signal off the microphone is coming through, and not only is it not a particularly strong signal, but it's kind of fuzzy, indicating that it's got a lot of noise around it. So that microphone signal could probably do with a bit of amplification. There's with a sawtooth waveform, and there's with the pulsed waveform. And let me just zoom out right here so that you can see that signal a little bit better right there. And you can see that by the time it gets into the microphone, that is no longer still a square waveform. It's lost a lot of that information that's going on right there. So noise and signal loss are a couple of things that can really be picked up and monitored with your oscilloscope. A very useful tool. And anyway, I'm going to turn off the function generator right now because that's really annoying. And just want to touch base on some of the main things that you're looking at on your scope. So the auto set button, well, your on-off button, your auto set button, if you've got no clue what you're doing, the auto set button can save you sometimes, but it's embarrassing if that's the only button you know how to push. The voltage control right here controls the range of voltage per division that shows up down here for channel 2. That shows up right down here. Okay. Pressing this button right here brings your channel 1 menu up. You want to make sure your coupling is in DC. Okay. For what we're doing right now, later on we'll take a look at the AC coupling. The ground is only good for figuring out where your 0 line is. Your trigger level is this yellow line right here. Moving that up and down helps you to lock that signal in place so it stays on the screen. There is a button that automatically sets it to 50% of your signal. A little bit of a cheat, you can do that. Your seconds per division over here controls how fast your little beam sweeps across the screen. And so when it says 5 microseconds per division, you're going pretty fast. At 5 microseconds per division, that's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 50 millionths of a second for that beam to get across the screen right there. Now, of course, it's not a real beam. It's a processed digital signal that's coming out of a whole bunch of amazing electronics taking place right in the back there. So we probably won't use channels 3 and 4 much at all this year, but if you do, they kind of work the same as channels 1 and 2. It's really useful to be able to use channel 1 and 2 to look at signals. Fancier features, the math menu that comes up here. You've got a print and a save button, and right down here you've got a USB output port. There's also a USB A port on the back, USB-C port. There's a USB port on the back so that you can plug it into a computer and you can capture these screens either to a flash drive or to a computer by hitting the print button. Along here, auto range helps you get things dialed in. This little dial right here can help you with some of the menus sometimes. That's what that's there for mainly. And there's a whole bunch of other functions under the utilities. Cursors for measuring things, measure tools for measuring things. All sorts of neat things that you can use to set up your display. But again, remember the run stop button. You need to be in auto mode down here. You need to be running. You can't be in the stop mode. And aside from that, play around with it and try taking some measurements, and you'll probably do okay. I'm going to show you a pretty cool application for the oscilloscope in just a moment. We can take a look at the quality of different USB charging devices.